Hey guys, so right now we're going to talk about the Bohr model. Now, one thing to keep in mind is that the Bohr model is not our current theory. It is a theory of the past, but it does help us explain some things about atoms that we wouldn't have been able to explain without it, so that's why it's important to go through this. So the Bohr model was created by a scientist called Niels Bohr, and he wasn't the first theory, he was somewhere in the middle. And the reason why he created a new theory was because he wanted to be able to explain how an atom changes or how electrons change when it absorbs or emits light. And so there's an energy change, and none of the previous theories were able to state this. Now, this is similar to the previous theory, Rutherford's model, saying that protons and neutrons are in the nucleus, and today we still believe that, and that electrons are surrounding it. Now, again, we still believe that electrons are not inside the nucleus, that it is surrounding it. But what's special about Niels Bohr theory, the Bohr model, is that he said that electrons were in specific orbits that circled around the circled around the nucleus, just like our planets circle around the sun. So that's kind of how he was proposing this. Now, he was saying that each of these orbits have a very specific energy level. And so at these different energy levels, only electrons with that energy were able to be on that energy level. So if we absorbed light, so if this atom absorbs light, then those electrons would gain energy. And so instead of staying on that specific orbit, it would have to jump up to a higher energy level. That's called the excited state. If something gains energy, in this case it's an electron's gaining energy, and instead of being where it was, it gets excited and gets pushed up to the next energy level. Now, you can't stay excited very long. You can't stay with a lot of energy very long. So eventually, that energy has to go away, and we say that energy is emitted. Now, energy is emitted in the form of light, and we will be talking about that. But when that energy goes away, that electron does not have as much energy, well, then it cannot stay at the higher energy level. So what happens, it drops back down to its original energy level, which is what we call the ground state. So this is what we need to know about the Bohr model. So let me show you an example of what a Bohr model looks like. I'm pretty sure you have seen Bohr models before, so we're just going to go through it quickly, and then I'm going to show you how this is going to apply to this class. So in the center of a Bohr model, we have protons and neutrons. So we can write protons is equal to and neutrons is equal to. And depending on the element that we're talking about, well, our protons and neutrons will change. Now, on the outside of our nucleus, we have electrons. So we have different energy levels. Our very first energy level can only hold a maximum of 2 electrons. So let's say that we have an atom that has 2 electrons, so we would represent both of these 2 electrons on the very first energy level, which we would call n is equal to 1. So our first energy level is n is equal to 1. Now, say if our atom that we're dealing with has more than 2 electrons, then we need to add on an additional energy level. Notice how we started at the first energy level, and once we exceed that, we have to go on to the next. Our second energy level is n is equal to 2, and that can hold 8 electrons. So let's say that this particular atom has a total of 14 electrons in it. We already have 2, so we need to keep building. So like I said, this can have a total of 8 electrons in it. So we already have 2, then 3, 4, 5, 6, 7, 8, 9, 10. Well, I've exceeded the amount of electrons that can be on my second energy level, so that means I need to add another energy level. Our third energy level is represented with n is equal to 3. Hopefully you're catching the pattern. Now this energy level can also hold 8 on it. So we already have 10, and we just need 4 more. Notice how I'm not putting all these electrons right next to each other. You want to set them up in groups of 4, and then you can double them, but don't just squish them all up here. Okay, so that's what a Bohr model would look like if I asked you to draw a Bohr model. The other thing that we have to be able to interpret is the Bohr model of a hydrogen atom, and that is found on the very first page of your reference packet. Okay, so please go ahead and take out your reference packet so you know what to look at. I'm just going to zoom in a little bit here. Okay. So here we have the Bohr model of our hydrogen atom. Notice how it says that our measurements are in nanometers. So the measurements that we're talking about here are these different measurements. And these are going to be wavelengths of light, which again we'll be talking about very soon. Just like on the Bohr model that I already drew for you, we have our different energy levels with our nucleus in the middle, and our electrons are represented by dots. What this is telling us is that, for instance, we have this electron that is starting on the 4th energy level. Well, what's happening here is this electron is going from the 4th energy level all the way down to the 1st energy level. So that means that it's emitting energy, it's losing energy. So when it does that, when it goes from the 4th energy level to the 1st energy level, if we follow this line all the way down, it will tell us the wavelength of light that is being given off. It's giving off a wavelength of light of 97 nanometers. Now, once we have the wavelength of light, we can figure out the type of light it is based on the section that it falls under. So here, if we have 97 nanometers, that is an example of ultraviolet light. Then we have visible and we have infrared as well. Now we can even take this a step further. Here we have the electromagnetic spectrum. The electromagnetic spectrum tells us different types of lights other than just these 3. So we have radio waves, microwaves, infrared, UV, X-rays, gamma rays. The reason why this becomes important is if we fall someplace in the visible light, so say if we had an electron that was transitioning from, let's say this is the 4th energy level down to the 2nd energy level, we would see that it has a wavelength of 486 nanometers. Well, a question that I can ask you is what color light is given off when an electron transitions from the 4th energy level to the 2nd energy level? So you would have to say, okay, 486 nanometers. Well, our electromagnetic spectrum is in meters. So we know that the conversion factor between meters and nanometers is 1 times 10 to the 9th. So we would have to convert this into nanometers and figure out what we get. When we do that, we should be able to say that that is 4.86 times 10 to the negative 7th meters. So what we would do is we would go down to this visible light now and see, well, what range does this fall into? 4.86 is between 4.9 and 4.2, so we can identify that we have blue light. So these are the types of problems you're going to be seeing for a Bohr model.